Hi class, and welcome back to another lecture video. In this lecture video, we're going to cover section 7.5, conditional probability and the independence events means. Okay, so first, let's take a look. What is the conditional probability here? Okay. Oops, I don't want the red. Okay, so let's see here. So the conditional probability. Okay, so first let's take a look at what is the definitions we defined as the conditional probability. This is how we write this here. Is a event E given F. Okay, so this is how we say it's a conditional. So the way we say it, this is the probability of event E happens given that event F already happens. Okay, so this line here, this line we read as given. Okay, so that's how do you read it? The probability of an event. So the probability of an event E happens, given that event A, event F already happens here, right? So this line, that's how we read it here, is given. And then the event F, this is we call it, this is our conditions. Okay, so that's how do we define the conditional probability. Okay, so for examples here, so if you say, what is the probability? Okay, so what is the probability you will take a nap given that outside is raining? Right, so for this statements here, so it's what is the probability you will take a nap given that outside is raining? So what do you see here? So your conditions here is I'm going to take a nap or not. So it depend on this condition, it's raining or not. Right? So basically for this statement, if you want to change to the conditional probability statement, it really is like this. You will take a nap. Right? So I want to find the probability I'm going to take a nap. Get a line. So that means given outside is raining. Okay? So that's what we call is conditional probability. So right now, I'm going to write out the formula. But before I write out what is the probability of E given F, right? So if you take a look, and then I think this formula will make sense here. Okay, so let's take a look here. This is your event E, the red one. Okay, now you take a look here. This is your event F here. Okay, so the way we read this probability is the probability of event E happen, given that F already happens. So for here, I know that F already happens. So that means here. It's under these conditions. So F already happens. Then what is the chance that A the E going to happen, right? So under the F is already happens. So what is the chance E going to happen? That's really, we are looking for this part, right? So the E is happen under the probability the F already happened. So basically, your sample space really changed to the F because F has to happen first, right? So that's what is your formula going to be, the P to the F. And then here, what is this red spot? This red spot is what we have been very familiar with, is the E intersections of the F, right? So that's how do you see here. So we said the condition, the F already happened. That's why, you have the denominators here is F, because it's under the F, what happened to the E. So under the F, what happened to the E will just be this little sections here. And this little section is the E intersection of the F. So that's what is our, so this is how we defined our conditional probabilities here. Okay, so you put your condition on the denominator, then the top, because you are under the F, the E to happen. So it will just be that little area is the intersection areas here. Did you get it? Okay, so now let's try to take a look at some examples and how do we use this conditional probabilities here, right? Okay, so these examples here. Okay, so we given that. Okay, so we given that PE is equal to 0.4. And the PF is equal to 0.5. And the P, the E union F is equal to 0.7. So I am looking for what is the conditional probability E given F. Okay. So now, in order to do this type of the problems, probably will be easier. So let's do a graph here. Okay, so here, take a look here. So this is your E, right? And this is your F. I know here, take a look at this one here. This one tell you the E and the F, E union F is equal to 0.7. So we know what is the union means, right? That means if you combine these two, so the yellow area is 0.7, correct? That's what is the union mean, okay? And now, we need to, because we need to first things here, from the previous page, from the formulas, right? So based on the formula, so based on the formula, the probability of the E given F, we just wrote on the previous page, is the PF. Then here, this is the probability E intersection F. So we have the PF. PF here, the problem given is 0.5. Now we want to find the E intersection F. That means right now I'm going to find the intersection. So this is the intersection part. If I can find this blue area, then I will be able to find my conditional probabilities here. So how do I find this blue area? Then we remember, right? So the recall here, we remember from the previous section, we call this the additional rule. So we call this addition rule. So the addition rule tells us, we say, hey, if you unit two things, right, will just be you add add each individual one. Then you minus, you intersect F here. Good, right? So now the problem gives us the union. So the union, the problem gives us is 0.7. And the problem gives us the E, right? So the PE is 0.4. So that's why this is a 0.4. And also problem give us the PF. PF is 0.5. So I plus 0.5. Then I'm looking for what is this common areas E intersection F. So now this will be 0.9 minus the probability E to the intersector F. Right now you minus 0.9 minus 0.9 both end. So you will get a negative 0.2 is equal to the negative P, the E inter F. Then you divide it by the negative 1 both sides. So you will get the probability of the E intersect F is 0.2. That's how did you find these areas, right? So this blue area is 0.2 here by using the addition rule. So now I know this area is 0.2, so I can put the 0.2 here. So that's why this conditional distribution is 2/5 or is 0.4. Because that's why when the F happened, right? So when F happened, what happened to the E? So that's why you put the F on the denominator, then you need to find the intersection. So how do we find the intersections here? That's why we use the additional rules, right? Addition rule, that's what this is the rule we discussed in the section 7.4, right? So if you don't remember, you need to go to the section 7.4 to review it. That's how do we do the condition. So remember your conditions is the events after that vertical line. And you put your condition on the denominator, then the numerator will be what is the, the intersection of these two events, okay? All right, so now let's take a look at so we'd also talk about, in this section, we already know, last section, we have the addition rule, complement rule. So in this section, we're going to talk about, we call this the product rule. So what is the product rules, okay? So the product rule, if you take a look, we talk about the E and F, right? We said E given F is equal to probability of the F, then the probability of the E intersect F. All right, so the intersect, so if you times, so if you multiply probability of the F on both sides, let's see what happens here. So if you times both sides here, right? So this will be probability of the F times the probability of the E given F will be equal to probability of the F, probability of the E given F times the probability of the F. All right, so this one cancel. So that's why you will get, this is the probability of the F times probability of the E given F is equal to probability E intersect F here. Okay, so this is what we call is the product rule. So basically the product rule will tell you, so if you want to find the intersection of the two events, right? So this is the product rule. It will be basically will tell you, you can use the PF and then times the probability of E given F here. Or they will also be equal to if you treat the E is the condition. So this will be probability F of a given E, right? So the reason why is because if you do this is the probability of the F given E, this will be equal to the probability of the E, and then this is the probability, the intersections. Did you see here? So the top is the same, right? Is E intersect B, E intersection F. So that's why if you times the PE both sides, so if you times the PE both sides, you will be equal to PE times of the PF given E, and then the PE upper F, right? So that's what we call this is the product rule. The key word for the product rule is here, right? So this is the intersect. So we know the key word is like and. So when we say E and F, so most likely you will, you will use the product rules, right? So the product rule, so you use your condition, and then you times your conditional probabilities here. So this is very, very important, right? So this is what we call this the product rule, and make sure you write it into your formula worksheets. You get that? Okay, now the next things here we're going to talk about is the independent. Okay, so what is the independent mean? So the independence means, so if, like if we say event E and F, they are independent. What's that mean? It's just like say you and me are independent. What's that mean? Right? So that means the behavior of event E will not change the behavior of event F here, right? So that means if A happen, if the E happen or not, well, has nothing to do, we're not affecting the event F, right? So that means they don't have any relation. They don't, will not change whatever the event of the F will happen or not. So for examples here, right? So for examples here, let's use like these examples here. Let's take a look at what is independence means here. So, for example, event E is I will go vote. I will go to vote this year, right? Then event F here is you will go to vote. So basically, since I'm not going to influence you and you're not going to influence me, so I will go to vote and you will go to vote. They are is the independent events. So if the probability I will go to vote is only 80%, will not change whatever the probability you will go to vote, right? So that's why, so I said, okay, so if you want to say, hey, what is the probability you will go to vote, given that I will go to vote? The problem is whether I go to vote or not, it doesn't matter. It will not change you. So if we are independent, right, that means even you give me this condition, it doesn't matter because we are independent. So this condition will not change your probability. So this will be F here. That's what we mean, the independent, because these conditions here, right? So that means this condition, this is the condition. is not affecting the probability of F, right? So that's why, the condition is just is there or not is there, doesn't matter anymore because we are independent here, right? So that's a very important concept. So like in here, I'm going to write down the independence here. If you understand, if you kind of is like a common sense, right? So in here you say if E and F, they are independent. Let's take a look at this one. If the E and the F, they are independent, then let's see what is the probability of the E given F. So remember that F is a condition. So let me see if the condition happen or not has nothing to do because they are independent to whether the E happen. So this will just be E. So if E will go to vote, they will go to vote. If E not go to vote, will not go to vote. It will have nothing to do with whether F go to vote or not, right? So that's what we call independent. So the same ways here. So the same ways here, if the F given E, so if now the E is the conditions, so if the E is the conditions here, then it doesn't matter, right? So it will be the PFs here. Okay, so now we arrive a very important. So if they are independent, then probability of the E intersection F, right? From what we did here, right? So this will be your condition times the conditional probability. But now, since they are independent, so this will just be the probability of the E times probability of the F. Okay, so that's why this is what we mean here. That means if they are independent, right? So then the probability of the E times the probability of the F will be equal to probability of the E intersect the F's here, right? So this is the super important things, right? So if they are independent, right? So if they are independent, then the intersection will just be equal to times to each other because then the conditional probability does not make sense anymore because they are not, the influence any others, right? Okay, so now, let's take a look, right? So let's take a look here, right? So some example about the condition probabilities here. Okay, so the important formulas for this page is here. First, you need to know what is the product rule. Okay, so you use product rule to find the intersection and based on the conditional probability. Then this is the special case. Remember, this is the special case. That means when both of these two events, they are independent, then what happened to the intersection become true. Okay, so now let's see here, right? Okay, so remember the key word here is and, all right? Okay, so now here I'm going to give examples here. Okay, so if two cars are drawn without replacement. What means without a replacement? That means after you get the first car out, for example, you draw the first car is a queen of the 10. Then you hold the car. You don't put the car back to your deck. That means after you withdraw one card, then the next time you draw, you only have 51 cards there, all right? So without the replacement from an ordinary from an ordinary deck. Okay. Then we want to find the following probabilities here. Okay, here. So the problem here, I want to find the probability. The second one is red, is a heart. Okay. The second one is a heart. Given that the first one, given that the first one is a heart. Okay. So the first one is a heart. Okay, given that the first one is a heart. Okay, so in here, you immediately see the keyword given. That means it's the condition. So let's put it into the probability statements here. So these ones here, that means that the second one is a heart, given that the first one is a heart. So the first is a heart, right? So given that the first is a heart. Okay, remember this is how we read is given that the first one is a heart, right? So when the first one is a heart, okay, so here now let's try to put it into the statement. So we say it's a P. So this one you put the condition on the bottom. So this is a first. So this is a first is a heart, right? So this is a first is a heart. Okay, now this one's here is a E and F, right? So this is the first is a heart and second is a heart. So and the second is a heart. Okay, so now let's take a look. How do I find the probabilities here, right? So in here, so the first one is a heart, right? So the first one is a heart. I know I have 13 heart. So the heart out of the 52. Okay, so I have a 13 heart, and so the chance for me to get that is 13 out of the 52. Okay, so now I'm going to take a look here, right? So the first one is a heart, given that the second one is a heart. So first one is a heart, right? So here we hear the end, the second one, that means the intersection, right? The second one is a heart. So the first one is a heart, I know is 13 over 52. Then after you draw the first one, then you only have 51 cards left because it's what? Because it's without replacement. So you don't put it back. And then because you already draw one card, so the second card is red, is a heart, you only have 12 left, correct? Okay, so now you can go boom, boom, and cancel. So that's why the answers here will be 12 over 51. If you simplify it a little bit, reduce the fractions, 4 over 17 here. Okay. Right, it's kind of makes sense, right? So you say the first one is a heart, so you have 12 heart left, and then the second, that's why the second one is a heart, so it's it's like 12 or 51 here. Okay, So let's see here, and then the part B is here. So the problem is a little bit different, right? So I say a jack, right? A jack and a 10 are drawn. Okay, so you want to find the probability. The first one is a jack, right? So that's why this way, this one you translate that is the first one is a jack, right? So here, so that means that the first card is a jack, and that means intersection, and the second one is a 10. Okay, so now let's see here, how do we do it? So if the first one is a jack, I know because I said inter and, right? So and you do multiplication rules, right? So that's why we said first is a jack. We have a 4 jack out of the 52. After you take a 1 jack, right? So you only have a 51 cards left. Then the second one has to be a 10. So you have 4 tens left, right? So it's a jack and a 10. And also, the reason then we also times 2 here. Why? Because this one can also be, so this one can also be probability. The first one is a 10. And the second one is a jack, right? So the problem just tell you, hey, it's a jack and a 10, right? So they did not tell you which one is which. So you add these two together, right? So that's why you add these two together. So it's the same. That's why in here you times 2, because you have 2 situations here. Okay, so now let's take a look at a few more. I think then you will get a better idea. See here. How about if I say I have 2 black cards? Okay, so the 2 black cards, that means what you have here, your first is a black, and the second is a black, right? And the and, we know the and is the keyword we use multiplications. So here it will, the first is black. I know I have a 26 black card because we have a spade and the club to be the black, okay? Then the second one has to be black also. So this one is 51. After you draw one, then this is 25. Right? So here we don't need to times 2 because it's a black and the black. You know, the order does not matter, right? So that's why we have, so if you simplify this a little bit, I think we have 25 over 102. Okay, so this will be the answers here. Let's take a look at the another examples here, okay? Okay, so let's take a look at examples. Another, the last part here, these here. So let's say here, I have 2 hearts. I want to find the probability of 2 hearts. Okay, so that means the probability, the first one is a heart, and the second one is a heart, right? So the first one is a heart. I have 13 hearts of the 52. Then after you take one out, you have 51. Then you have 12 cards again, right? So that's why this answer will be 1 over 17 here. Do you see that? So that's why every time you see the keyword, like we said, the keyword here is and, right? So when you end, okay, so you find that. Okay. Okay, let's try to do another example. Some of your homework problems will be similar like this. So be careful for the conditional probabilities, right? Okay, let's try to do one more. I think then probably you will get a better idea. So this is the example 3. Okay. So the following, so we have a following table. The following table shows the frequencies shows the frequencies for the colorblind. This is for red and green colorblind. Okay, so let me draw this table for you. So this tables here, this is what we call this is the male, okay, M-A-L-E, and then we use the M to represent, right? And then here, this one's here, we say this is the female, or we say this is the like the imprints here, right? So it's nothing, not in the ends, right? So this is the color blind, and then C prime, that means it's not the color blind. So the probability here, this is 0.035, and this is 0.452, and this is 0.004, and this is 0.509. All right, that means here. So you summarize this table. So here, this is the total. So this is 0.487 and the 0.513. When you add them up, it's 100%, right? So it's 100. And here, this one, if you look at the total from here, it will be 0.039, and this is 0.961 here, all right? So now let's take a look. So like for here, if we say, hey, what is the probability of the N? That means what is the probability for this survey? And we find it's the male. So the male, you look at the male columns, right? So the male column, so this is what the male column is, right? So you add that up. So what is here? So this will be the 0.487, right? So now another one is here. So the male, so this is the males, right? So this is the male. So this column is the males, right? So that's why total we have a 0.487 male. Okay, so how about if I want to find out what is the percent of the colorblind, right? So the percent of the colorblind, so you're only looking for this ones here, right? So how many, what is the percent? It's 0.039. So it's about 3.9% here. Okay, so now let's take a look at this one. So probability of the male and cis here. Remember the male, right? So this is the male. So remember what is the intersection mean? The keyword is and, right? So that means male and the colorblind, right? So here, this one's here is the male and the colorblind, correct? So that means the male and the colorblind is 0.035. You get that? Okay, so now let's take a look at this one to see if we can get that. So we say probability of the male given C. What's that mean? That means what is the probability? I know this person is colorblind. Given the person is colorblind, what is the chance to be a male, right? So then we say here, we say use the conditional probability. You put the conditions, right? So in here, I know this one is my condition. The colorblind is my condition. That means that the person is colorblind. Given that it's colorblind, I want to find what is male. What is the probability this person is a male? So that means you use the probability M intersect C. That's our conditional probability definitions, right? So the probability of the C is the colorblind. We just did that. It's 0.039. The colorblind and the male is 0.035. Then if you do that, so this is 0.897. That's how do you interpret this one? That means, the male is the majority of the colorblind. So if you find a person is a colorblind, then it's almost 90% of the chance this person will be a male. For some reason, I don't know, the genes kind of like, the male's gene. So majority of the male is a colorblind. So that's how do you interpret the 0.897. That means if you find a person is a colorblind, so what is the probability this person will be a male? It's almost 90%. So it's 89.7%, right? Okay, so if you want to find the part E here, so they say, what is the probability of M prime C? That means if you find a person is a colorblind, what is the probability this person will be a female, right? Then you use the same things here. You say, okay, I put a condition on the bottom. Then the tops here will just be the M prime intersect the C primes, right? I'm sorry. So probability of the colorblind is 0.039. Then what is the M prime? That means what is what is the female and the colorblind? Where is that? Here, this is the female and the colorblind, right? So it's a 0.004. So this is 0.004. So now if you calculate that, it will give you 0.103. So that means the chance for female to get a colorblind is way, way smaller than the chance for the male to get a colorblind. This is how do we use the conditional probability, and that's what we talk about the conditional probability and the independence, right? So summary, okay? So combine the sections 7.4 and 7.5. So basically, we have only few formula to summarize, right? So the first thing here is addition rule. Okay, so the addition rule is a probability A union B is equal to probability of the A plus probability of the B minus the probability of the A intersect B. Remember, in the word problem, they're not going to tell you, say, use the addition rule. So you need to read the problem and find the keyword, right? So in here, when do you know you use the addition rule? You're looking for the keyword here, right? So the keyword for we call it is or. If you see the problem say A or B, so it's very possible you use addition rules, right? So that's why this is our keyword is or, right? Okay, be very careful. Like I said, in the word problem, they're not going to tell you, hey, use the addition rule, use the multiplication rule, those things. They're not going to tell you that. Okay, so then the next thing here is the multiplication rule. So the same way, the key word for the multiplication rule is you're looking for the word and. Okay, so that means you do like A intersect B will be equal to the probability of the A times probability of the B given A, or you can write as probability of the B times probability of the A given B, as long as you are consistent, right? Okay, so then the next one's here, we call it a complement. Okay, so complementary rule, also like I say, most likely they will not tell you, hey, use the complementary rule. So the key word you're looking for in the complementary word is not. In general, it's not. That means if not A, not B, then how did you find the probabilities, right? So this is like we say, the probability of A complement is not A, will just be the 1 minus the probability of the A's here. Okay, so also the multiplication rule have a special case. So here have a special case. So what is the special case? So the special case is A and B are independent. So if they are independent, then the probability of the A intersect B will just be equal to the probability of the A times the probability of the B. All right. Okay, so that's all about this chapter. So we talk some very, very basic probability rules, and so you might want to listen this video a couple times, make sure you fully understand this. All right. Okay, so that's it for this video about the section 7.5, and we finished chapter 7. So the next things we're going to do, it will be chapter 8. All right. Okay. So nice talk to you guys again, and so keep up with the good work, and so finish the classwork and the My Math Lab homework and listen to the video. Okay. Bye. Talk to you next time. Okay. Bye bye.